And when I'm looking at these exponential equations right here, the downside is I can't make the bases to be made the same. And by the way, that's going to be the normal thing that's going to happen. That's normal. It's more unusual that you can make the bases to be the same. That's book problems. When you look at application problems, it's going to be very likely that they're not going to be able to be made the same. But I think this is where logarithms ended up coming from, is that when you need to solve an exponential equation, what you need to do is you need to get your hands on that exponent. Because you want to solve for x, which means you need to undo the exponential function. And the exponential function that would undo this guy, or it would be the function that would undo this exponential function is logarithm. Unfortunately, and log base 2 would nicely undo it, except I don't have log base 2 on my calculator. I only have two logs. I have natural log and I have log base 10. So we would use one of those two, and then I'll use our calculators to actually get out a numerical value. And it goes back to this particular idea right here. If I know that x is equal to y, if I know the two things are equal, I then also know that the log of x also has to be equal to the log of y. We can go one of two ways. If I had two logs equal to each other, then x equals y, and actually I can put arrows going both directions. Or if I know the two things are equal to each other, then the log of those two things have to be equal to each other. Now, what's the benefit of that? If on this side of the equation I had a logarithm, the properties of logarithms enable me to bring the exponent down in front. And what that means is I can get the exponent out of that little top and move it down to the baseline. So that means I know these two are equal, so I just pick any log, doesn't matter, so that I know that the log of the left-hand side equals the log of the right-hand side. The left-hand side is 2 to the minus x, and the right-hand side is 1.5. So if those two things are equal, then the log, and I'm using log base 10 because that's on my calculator, then log base 10 says that I can then take the log of both sides. They're equal. Now that enables me then to take the exponent to bring it down in front so that the opposite of x times log of 2 equals the log of 1.5. Now right now everything is exact. The minute that I put any of the log, because these logarithms are now numbers, the minute I calculate out numbers, I'm going to do an approximation. Because if I look at log of 2, the log of 2 is 0.301029997. And the log of 1.5 is also a decimal number. If it would make you happier, change those to decimal numbers and work them with just decimals. Then they're just numbers. Because that's all they are. But knowing that this is just a number and this is 0.301, I can divide both sides, because I want to have x, not the opposite of x, by a negative that takes care of the opposite, and the log of 2 that takes care of the log of 2. But whatever I do to one side, I must do to the other. So that means that x itself is the log of 1.5 divided by the opposite of the log of 2, and this is an exact answer. If you changed anything to decimals, then you would have an approximate answer. And I could calculate that out with my calculator. Now, in order to take the logarithm of both sides, I need to have the factor that's got the x in it by itself. And then you might say, well, why would you want to do that? If I were to try to take the log of both sides as it stands, so if I take the log of both sides as it stands, here's the problem. I can't bring the exponent down in front because there's a multiplication sitting there. And this 0.3 doesn't have the same exponent as that 4 does, so I can't bring it down in front. What I'm going to have to do is use the properties of logs to make this log 0.3 plus log of 4 to the 0.02x equals the log of 0.2 in order to make it work. So the goal is you find what's got the x in it and you get it alone and isolate it. Then you can take the log of both sides. Otherwise, it gets really nasty messy. So that means I'm going to divide both sides now by 0.3. So that 4 to the 0.02x equals 0.2 over 0.3, which is just 2/3. This is equal to 2/3. Now, what do I need to do? Well, I need to take the log of both sides. The log of the left-hand side, 4 to the 0.02x, equals the log of, if you wanted to do 0.2 over 0.3, that would be fine too, 2/3. And now the drill. Bring the exponent down in front, and it says that 0.02x log of 4 equals the log of 2/3. Now I only need the x. Since I only need the x, I'm going to get rid of the 0.02 and the log of 4, because that's a decimal number, and the 0.02 and the log of 4, which means that x is the log of 2/3 divided by 0.02 times the log of 4. That again is an exact answer. And I can calculate it out with my calculator if I like. This next one isn't pretty. It's probably one of the more difficult of the problems that you have to work like this. And why would I say it's not pretty? Because number one, you can't make the bases be the same, and number two, when you take the log of both sides, there's two terms for this exponent and there's two terms for that exponent. It's going to become really messy. That's when some of you might want to change to decimals. So if two things are equal, that means that the log of those two things have to be equal. Now, this is where, because we're in college algebra now, you have to learn to dot your I's and cross your T's. Because this is more than one term, when that exponent comes down, That's more than one term that's going to multiply that logarithm that's left. If I were to just write this, what I'm saying is take x and add it to 1 times the log of 2. But that's not what it is. The exponent was x plus 1. So it's x plus 1 times the log of 2. That's what makes this particular type of problem so ugly. Because I've got the same issue with the guy on the other side. I'm bringing down a 1 plus 2x. And this is going to be times the log of 5. Log of 2 is just a decimal number. Log of 5 is just a decimal number.
1 minus 2x.
Okay, 1 minus 2x. All right, thank you. So what do I do from here? Well, this is a number. Log of 2 is 0.301, so I could change this to 0.301 and you might be happy. Because all this is 0.301 and then this should be log. Why did I write natural log? I don't know. So log of 5 is 0.699. They're just numbers. So that's why I can manipulate them like they're just numbers, because that's what they are. So what would I do? Clear parentheses, because x is in the parentheses. So multiply through by the log of 2, I will get x log of 2 plus 1 times the log of 2 equals log of 5, 1 times the log of 5, minus 2x times the log of 5. Then what do you have to do? You got to get everything that's got a term that's got an x in it, and that's these two guys, together on one side, and everything that doesn't on the other. So I'm going to add 2x log of 5 to both sides. So I'm going to get x log of 2 plus 2x log of 5 plus log of 2 equals the log of 5. Now I'm going to move the log of 2 over by subtracting log of 2. So that x log of 2 plus 2x log of 5 equals log of 5 minus log of 2. Now you have a greatest common factor of x. So you can factor an x out, which is log of 2 plus 2 log of 5 equals log of 5 minus log of 2. And now divide both sides by log of 2 plus 2 log of 5 so that x is log of 5 minus log of 2 divided by log of 2 plus 2 log of 5. That's an exact answer. Not pretty. It's the ugliest problem that we end up doing.